Another application of trigonometric functions is complex numbers. These numbers have both real and imaginary parts, which can be represented in an orthogonal coordinate system. Complex math can be simplified by transforming the numbers between coordinate systems. This video covers complex numbers and their representation in rectangular and polar coordinates. Complex numbers consist of combinations of real numbers and imaginary numbers. Real numbers represent physically possible parameters. I can have 3 apples, for example, or a circle with a circumference of 4 times pi. Real numbers can include irrational numbers, so pi is a real number. Imaginary numbers, however, don't describe anything in the physical world. They're based on taking the square root of -1, which is indicated by either a lowercase I or a j. Physicists, most engineers, and mathematicians usually use I. In electrical engineering, I is reserved to indicate electrical current, so electrical engineers use j to indicate the square root of -1. I'll use lowercase j in this course. Since squaring any number results in a positive value, no real number satisfies this equation, and this number has no meaning in the real world. Any imaginary number can be written in terms of the square root of -1. For example, the square root of -4 can be written as the square root of 4 times -1, which is the square root of 4 times the square root of -1. Since the square root of 4 is just 2, this is just 2 times j. It doesn't matter which order these two numbers go in, since multiplication is commutative. So any imaginary number can be written as a real number, in this case 2 times either I or j. Keep in mind that j is not a variable, it's a number, and it equals the square root of -1. Considering that the square root of -1 has no meaning in the real world, engineers use it an awful lot. It turns out that imaginary numbers are really useful in lots of analyses. Even though they don't exist in the real world, they can make calculations that describe real-world phenomenon much easier. Applications include the analysis of mechanical vibrations, acoustics, and AC electrical signals. We'll see some specific applications of imaginary numbers later in this class when we talk about sinusoids. To emphasize that j is just a number, let's do some common operations using it. J squared is just the square root of -1, which is j squared. Square root of -1 squared is just -1. J times -j is the negative of j squared, so the negative of -1 is +1. Finally, 1 over j, I can multiply top and bottom by j, since I can multiply anything by 1 without changing it. This turns out to be j over j squared, which is j over -1, which is -j, so 1 over j is the same as -j. Complex numbers contain both real and imaginary numbers. For example, 5 minus the square root of -4 is the sum of a real number and an imaginary number. It's 5 minus j times 2. These two terms can't be combined because they're completely different types of things. Since real and imaginary numbers don't share anything in common, they're independent of one another, and they can be used to define an orthogonal coordinate system. Graphically, the real part of the number is displayed on the horizontal axis, and the imaginary component is on the vertical axis. This set of axes is often referred to as the complex plane. Any complex number can be represented as a point on the plane. If I have a complex number a that equals little a plus j times little b, I can plot that point as shown here. When I write a complex number in this form, it's in rectangular coordinates. I'm given the distances in the x and y directions on my axes. The real part of the number, little a, is the distance on the horizontal axis. The imaginary part, little b, is the distance on the vertical axis. If we have a complex number, capital A, that's equal to little a plus j times little b, it corresponds to a point in the complex plane in rectangular coordinates. The distance along the real axis, little a, is called the real part of the complex number. Mathematically, I'll write that as RE of a. The distance along the imaginary axis, little b, is called the imaginary part of the complex number, capital A. It's denoted as IM of a. Notice that little b is the distance on the vertical axis and does not include the j. J times b is imaginary, but b itself is a real number. The j just tells us which axis b is on. Next, I'll talk about representing complex numbers in polar coordinates. As usual, the point is represented as a magnitude, which provides the distance the point is from the origin, and a direction in the form of an angle from the positive x-axis. For complex numbers, an alternate way to express the number in polar coordinates is this. The magnitude is now multiplied by a term of the form e to the j times theta. E to the j theta is called a complex exponential. It still provides the direction information, but in this form, there's actually a multiplication process involved. In the original form, we're just presenting two pieces of information, a distance and a direction. Now let's look at a couple of specific examples of complex numbers in polar and rectangular coordinates. This complex number is in polar coordinates. It has a magnitude and an angle from the positive real axis. So this 2 means that our point is 2 units from the origin. The 45 degrees means that the direction is 45 degrees from the positive real axis. This number is in rectangular coordinates. 1 plus j2 gives us a real and an imaginary part. So the real part is 1. That means the point is 1 unit from the origin on the x-axis, and the imaginary part is 2, which means it's 2 units in the imaginary direction. The j just tells us that this 2 is associated with the imaginary direction. Some arithmetic operations, such as addition and subtraction, are easier to do in rectangular coordinates, while other operations, like multiplication and division, are much easier in polar coordinates. This means that conversion between coordinate systems can make complex arithmetic a lot easier. Understanding how to convert between coordinate systems is crucial to doing complex mathematics. First, I'll talk about conversion from rectangular to polar coordinates. A complex number in rectangular coordinates is in this form. It provides distances in the real and imaginary directions. The same number in polar form looks like this. It gives a magnitude and a phase angle, theta, from the positive x-axis. Conversion from rectangular to polar coordinates is the same as in previous videos. The magnitude is the square root of the sums of the squares of the real part plus the imaginary parts, according to the Pythagorean theorem. Notice that the imaginary part doesn't include a j here. The angle is the arctangent of the imaginary part divided by the real part, the opposite over the adjacent. Also, there's no j here. Always check the quadrant when doing the arctangent process. Now let's do a couple of examples of conversion from rectangular to polar coordinates. My first example is a is equal to -2 minus j times 4. So the real part of this number is -2 and the imaginary part is -4. To calculate a magnitude, I take the square root of the real part squared plus the imaginary part squared. -4 squared is 16, -2 squared is 4, so this becomes the square root of 20. Theta is the arctan of the imaginary part, -4 over the real part, -2, which from my calculator gives me 63.4 degrees. Now I have to check to make sure I'm in the right quadrant with this number. 63.4 degrees puts me up here in the first quadrant. The real and imaginary parts are both negative, however, so I need to be in the third quadrant. I can get to the correct quadrant by either adding or subtracting 180 degrees from this number. If I add 180 degrees, I get 243.4 degrees in this direction, or -116.6 degrees in the negative direction. I can choose either of these numbers. They're both the same angle. I'm going to choose -116.6 degrees. So in polar form, a is the magnitude, square root of 20 at an angle of negative 116.6 degrees. In complex exponential form, it's the square root of 20, the same magnitude, e to the j times the angle, which is negative 116.6 degrees. Conversion from polar to rectangular form is also the same as we've done before. These are our complex numbers in polar and in rectangular form. The real part, little a, is the projection onto the real axis. Since the real axis is adjacent to the angle theta, that means little a is the magnitude of a times the cosine of theta. Little b is opposite to the angle theta, so little b is equal to the magnitude of a times the sine of theta. Now let's do an example where c is equal to negative 5. This is a purely real number, so it can be expressed as negative 5 is the real part plus j times 0. The imaginary part is just 0. So the magnitude of c is the square root of the real part squared plus the imaginary part squared. The square root of 5 squared is just 5, so the magnitude of c is positive 5. And the angle of c is the arctangent of the imaginary part, which is 0, over the real part, which is negative 5. This gives me 0. The arctangent of 0 is 180 degrees. So c in polar form is 5 and an angle of 180 degrees. And in complex exponential form, it's 5e to the j 180 degrees. I can also do this problem graphically and skip all of these steps. If I plot c on a real imaginary axis, it's just negative 5, which is over here. This point in the complex plane is at 180 degrees, and it is 5 units from the origin. So from this graph, I can write directly c is equal to 5 at an angle of 180 degrees. Sometimes it's useful to think of complex arithmetic in terms of vectors. If we have a point A in the complex plane, we can define a vector pointing from the origin to that point. The vector has a magnitude A and a direction theta. The direction is denoted as e to the j theta. The same point can be defined in rectangular coordinates by vectors with magnitude a times the cosine of theta in the real direction and the magnitude of a times the sine of theta in the imaginary direction. The vector sum of these two gives us the vector in polar coordinates. Defining these vectors means we have to define unit vectors in their directions. In rectangular coordinates, we can think of the unit vector in the real direction as just being 1, since any real number is just its magnitude times 1. In the imaginary direction, our unit vector will be j, since an imaginary number is a magnitude times j. Performing a vector sum means that the magnitude of a times e to the j theta equals the magnitude of a times the cosine of theta plus j times the magnitude of a times the sine of theta. Dividing out the magnitude of a gives e to the j theta in terms of real and imaginary parts. This means that e to the j theta can be thought of as a unit vector in the theta direction. This equation gives the transformation between the unit vector in the theta direction and the unit vectors in the real and imaginary directions. Remember that 1 is the unit vector in the real direction, and j is the unit vector in the imaginary direction. Now let's do a couple of examples of conversion from polar to rectangular form. If I have a number, a, which has a magnitude of 2 at an angle of 45 degrees from the real axis, to convert to rectangular form, the real part is 2, the magnitude, times the cosine of 45 degrees, and the imaginary part, which multiplies j, is 2 times the sine of 45 degrees. The cosine of 45 degrees is 1 over the square root of 2. The sine of 45 degrees is also 1 over root 2. So my number becomes 2 over root 2 as the real part, plus j times the imaginary part, which is also 2 over root 2. As another example of conversion from polar to rectangular form, this number is in complex exponential form, 5e to the minus j 90 degrees. So I've got a magnitude and a phase angle. The real part of this is going to be 5 times the cosine of the angle, which is minus 90 degrees, plus j times the magnitude 5 times the sine of minus 90 degrees. The cosine of minus 90 degrees is 0. This becomes 0. The sine of minus 90 degrees is negative 1. So this becomes 0 minus j5. I don't have to express the real part if I don't want to. So b is equal to minus j5. I can also do this problem graphically. If I plot it in the complex plane, real and imaginary axes. This is at negative 90 degrees, which puts it on the negative imaginary axis, and it's 5 units below the real axis. So b from this is negative j5. That covers the basics of complex numbers and using trigonometry to convert them between coordinate systems. The next video is about complex arithmetic and why the choice of coordinate system is important.